Section 14.5, Nonlinear Equations. So, in this case, what we'll be doing is looking at systems of nonlinear equations and looking at solution to those for both equations and for inequalities. So first, before I do that, is let me just let's recall, if I happen to have, say, two equations in two variables, well, there were really only like three differing things that could occur. I could either have no solution, one solution, or an infinite number of solutions. So that's for the number of solutions. So I could either have two lines that were parallel, they never intersected, so I had no solution. I could have two lines that intersect, so I could have one solution. Or I could have two lines that are the same line, so they're two coincident lines, in which case I'd have an infinite number of solutions. And that was the only real the only real possibilities for the number of solutions: 0, 1, infinity, and that was it. Now let's suppose instead, but for nonlinear equations, we can have a whole bunch of differing sort of amounts of solutions. So suppose I have, let's say a parabola, and maybe, let's say an ellipse. Okay, so if you had some sort of ellipse and a parabola, well, you can certainly have no solution. So that's one possibility. Or you could have one solution. Here, let's separate this out so you can see how it's been separated. So I could have one point of intersection between maybe I should label this. This is my parabola, and this is my ellipse. And so here is my parabola. Here's my ellipse. And here's my point of intersection. So I could have one solution. Okay. Well, but in this case, I could have an ellipse and then a parabola. So I could actually have 2 points of intersection. So here's my parabola. Here's my ellipse. And so I could have two. I could have a ellipse and a parabola. And I could have it actually intersecting at 3 points. So here's my parabola. Here's my ellipse. And so, in this case, I could have 3 number of solutions. And really, that's about it. So, no, wait, 1, 2, 3. Oh, I can have 4 solutions. And so I could have it looking like this and like that. I could have 1, 2, 3, 4. So I have here a parabola, an ellipse. I could have 4 solutions. And so what you notice here is that for the case of nonlinear equations, It's much richer. The fact, you know, I could. So when I was talking about linear equations, you had 0, 1, infinite number, and that was it. When you're talking about nonlinear equations, they can have a whole bunch of a variety of the number of solutions. And so it's not an arbitrary amount, but it's certainly not only 0, 1, infinity. It could be other cases. You know, you could have, like in this case, 4 places that are intersects. Okay, so um, let's also recall techniques for solving systems of linear equations. For solving systems of linear equations. Well, our techniques were graphing, substitution, elimination, the matrix methods, and determinants. Well, if you recall, it was very difficult to actually use graphing in the case of linear equations. So in the case of nonlinear equations, it'll even be more difficult. So in general, I'll say you should be guided. Just like here, we were guided to know sort of how many solutions are available, but we don't really use it for a technique. Matrix, or maybe I should make these red. The matrix equation, using matrices or determinants are not really applicable at all for solving nonlinear equations. We'll usually use elimination. We may sometimes use substitution, but it'll usually be elimination. So the majority of times we'll be using elimination. Okay, so let's do some examples. Let's say on page 620. Why don't we do problem number 2? Y equal x minus 1, y squared minus 2x minus 6 equals 0. Okay, so this is, maybe I'll call this R1, R2. So you notice that the R1 is just a line, and well, R2 is a parabola. So you have a line and a parabola. Well, you could either have no solution. So I guess I'll just list the number of solutions. So you can have no solution. You can have, well, one solution, two solutions. And really, that's about it. 0, 1, 2 number of solutions. Those are the only real possibilities for having having intersections between a line and a parabola. Okay, so we can only really have one of those. Okay, so let's do substitution, I guess. Let's substitute R1 into R2. And so I'm going to replace y by x minus 1 and solve for x. So I get x squared minus 2x plus 1 minus 2x minus 6 is 0. And so I have x squared minus 4x minus 5 is 0. I can factor this. This is a monic quadratic. Bring down the negative times negative is positive. I want two whole numbers whose product is 5 and whose difference is 4. 5 and 1. Set each factor equal to 0. and solve for x. Add 5 to both sides of your equation and subtract 1. So x is equal to 5 or x is equal to negative 1. Now, before when we were doing linear equations, I just said, well, x is something and y is equal to something. You cannot do that for nonlinear equations because there could be more than one solution. And so you have to match up your coordinates, your x coordinate with the y coordinate of the differing solutions. And so when x is 5, let's figure out y. So I can use R1. And so y is equal to x minus 1, 4. And, well, for this other case, y is equal to a negative 1 minus 1, negative 2. Therefore, I have two solutions, 5, 4, and I have negative 1, negative 2. And so I have two pairs of solutions. So it was, well, I could have two solutions, good. So it was this case where the line intersected the parabola at 2 points. Okay, let me do problem number 10. And so x squared plus y is equal to 2. X squared, x to the fourth minus y equals 0. So let me add these two equations. In that case, if I add these two, the y's are going to cancel. So I'll get x to the fourth plus x squared equals 2. Subtract 2 from both sides of my equation. And so x to the 4 plus x squared minus 2 is 0. Let me try to factor this. This is quadratic in form. It's quadratic in x squared. It is a monic quadratic in x squared. And so let's try to factor this. So this is x squared dropped on the plus times minus is minus. I want two whole numbers whose product is 2 and whose difference is 1. So 2 and 1. Set each factor equal to 0 and solve for x. Subtract 2 from both sides of your equation. Add 1. So x squared equals negative 2. X squared equals 1. Well, I can't really have that x squared is equal to negative 2 because then I'd have complex solutions. And, well, I don't want complex solutions. And so in this case, I will discard the complex solutions. So x squared is equal to 1. Therefore, x is equal to plus or minus 1. And so let's figure out what y is equal to. And so in this case, y, so from R1, I guess, x squared plus y is equal to 2. So 1 plus y is 2. Subtract 1 from both sides. And so y is equal to 1. And so my two solutions are negative 1, 1 and positive 1, 1. Okay. Let me do problem number, let's say 14. X squared over 12 plus y squared over 16 is 1. 3x squared over 35 plus 2 y squared over 35 is equal to 1. Okay, so let me do that. And so, first off, maybe what I'll do is I'll multiply by 35, multiply by, let's see, that'll be 48, to get rid of all the denominators. So I get R1, 4x squared plus 3y squared equals 48, R2, 3x squared plus 2y squared equals 35. Okay, so now, I don't know, let's get rid of the y squares, I guess. And so let me multiply the first equation by 2, negative 2. And so negative 8x squared minus 6y squared equals negative 96. Let's multiply the second equation by 3. 9x squared plus 6y squared equals 105, and let's add. So you get x squared, 9x squared minus 8x squared is 1x squared. The 6y squares cancel. 105 minus 96 is 9. And so I get that. So that's what x squared is equal to. Let's figure out what y squared is equal to. Then I'll figure out x and y. And so I guess I'll use R2. And so I get 3x squared plus 2y squared is 35. So 27 plus 2y squared is 35. Let me subtract. Subtract 27 from both sides of my equation. And so I get that 2y squared is equal to 8. Divide both sides of my equation by 2. So y squared equals 4. And so x squared is 9, y squared is 4. So in this case, it actually has 4 solutions. X can equal negative 9, y could equal negative 2, x could equal negative 3, y could equal 2, x could equal 3, y could equal negative 2, x could equal 3, y could equal 2. So in this case, there are actually 4 solutions. And there they all are. Last, let me do problem number 18. X squared over 36 minus y squared over 36 is greater than 1. Well, the boundary line will look like a hyperbola. So notice that this is going to be a dashed line, and the boundary line will be a hyperbola. And so let's do this. So I have here x, y. And so A in this case, so the center of the hyperbola is the origin. A is 6, B is 6, C, 36 plus 36 is 72, which is 6 rad 2. And the asymptotes, well, the vertices are at plus or minus 6, 0. The foci, plus or minus 6 rad 2, 0. The asymptotes are at y is equal to plus or minus x. Okay, so let's do this. So 6. Let's just see if I can do it. 1, 2, and zeros. 1, 2, 3, 4, 5. Okay, so let's do it. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. Okay. Let's draw my asymptotes. Draw my asymptotes. Okay. And the x is positive, and so it's going to be here. We will approach the asymptote, and it will not be included. So it's a dashed line. It's a dashed line. Approach another dashed line. Okay, so now I got to figure out where to shade. I may even go for a semi-bigger one. Okay, so, oops, but notice first. Let's check. No, I don't need to go that far, so let's do new page. Let's check at the origin. I guess I need just, I'll do that for a second and then get rid of it. So let's check at the origin. And so is 0 squared over 36 minus 0 squared over 36 greater than 1. So is 0 greater than 1? No. So therefore, the origin is not part of the the solution set, and so everything out here is in the solution set. So let's see how much I can cover. So all this stuff, all that stuff is in the okay. So now let's see if I can draw this. I went over a little bit too far. Let's fill in all that stuff. Let's fill in all this. Okay, let's see how much I can. Okay, good. And there, that looks pretty good. Yeah. Try that. Okay, not too bad. That's a little off. Okay. Okay, strangely, it went over on that area. And let's keep going on this. Good enough. This just goes in a strange direction. When I get over here, try to fill this in. I bled over a little bit too much. And let's try here. Wow, that's jumping in such weird directions. Okay, so let's see if I can get rid of any of this. It's jumping, it doesn't even register. Okay, in the area. See if I can. Okay, sorry. Good enough. I'm never going to get that last area. Well, I might be able to get a little, do it that way. Okay, good. So that is the solution. Okay, so that's the solution. So notice it does not include the boundary. The boundary is dashed. And that is the solution of my system of nonlinear equations. So that really finishes off section 14.5, which finishes off chapter 14. And that is it for today. So let me stop this recording.